Yes. So let us again recall. We tried to do a Bayesian inferencing, that is, find out the probability p theta, which are the parameters given the data x, and we saw that using Bayes rule, it is a product of the likelihood p x given theta into the prior theta divided by the evidence x. The new denominator is the evidence is a integration, which is a marginalization over all values of, and this is difficult to compute, and often the intractability is due to this denominator. So the posterior distribution p theta given x, the numerator of it we know, the denominator, which is the normalizing constant, let's call it z, that we don't know. So let us denote the numerator by p tilde theta given x. So it's not exactly a distribution, not exactly the posterior distribution. It is an approximation of the posterior distribution up to the normalizing function. And these two we know. So p tilde we basically know because we know the likelihood as well as the prior. So we'll say that we'll use the terminology that this is the posterior distribution p tilde up to the normalization factor. Okay, we are ignoring the normalization factor. So our goal is that given knowledge of p tilde, can we kind of reconstruct or get back the actual posterior p theta given x? We'll see that this can actually be done using several approximate Bayesian methods. One of the methods you already saw is the variational inference. That means you have an approximation Q for the full posterior p theta given x, and Q is constructed by an optimization procedure which uses p tilde, not p theta. Okay, so the second approach is based on sampling. So just to look at things pictorially, this is the original distribution. Let's say it is a complex distribution with say two modes, and this red line is a mean field variational inference approach. So if you remember the variational inference approximation, the problem was that moment you make mean field assumptions, it's difficult to approximate multiple modes. So since it minimizes the KL divergence, it focuses on the high probability region of the original distribution, that is focuses near the mode values of the original distribution, the dominating mode of the original distribution. So you will get something like this. If you are only interested in the high probability regions, this is a good approximation, but if you are also interested in the low probability regions, then maybe this is not a good approximation. Another way is that if we can somehow draw, somehow within quotes, if you can draw a large number of samples from the original distribution. So one more thing I'll do is that by this original distribution, I will usually mean this posterior p theta given x. But in general, it can be any distribution. So just for for the sake of notations, I am writing it as I'll write it as just px, some distribution px. So if you can draw some samples, large number of samples from the original distribution px, sometimes called the target or the desired distribution px, then we can express it as an approximation in the following form. So at each of the sample points, you draw a delta function. Right? And the actual distribution is kind of the collection of all these delta functions. It's the collection of all these. So you see, if you get a large number of samples, you will gradually start approximating it well. Okay. So, so one thing is clear that if we can get a good sample, we can reconstruct the distribution. But the challenge is getting a good sample. because this distribution, as you have said, is intractable. We don't have access to this distribution. We could not calculate or compute this distribution. Okay, so how do you generate a sample from a distribution which is intractable? Today, we'll study two techniques which will allow us to draw samples from a intractable or a complex distribution, provided we can draw samples from a simpler distribution. So for example, if you can draw uniform random numbers, you can repeatedly call that uniform random number generator to generate a sample from a complicated distribution. Okay, or maybe if you have so this is what we have a target distribution which is intractable or maybe known only up to the normalizing constant. So you only know the p tilde version of that. Can you use another known or standard distribution? Use it repeatedly to draw a sample from the target distribution. And this known or standard distribution, this can be a standard random number generator available in most programming languages, or it may be some random variable distributed according to the standard normal distribution. Normal distribution centered at 0 and with variance 1. Standard univariate normal distributions. Actually, many programming languages will also provide you a function to draw a random number distributed according to normal distribution in the range 0 to 1. Okay, so we'll use that repeatedly to draw a sample from a complex distribution. Let us first consider a simple strategy. Okay, let's say our target distribution is univariate. So there is only one variable x, and the target distribution is this red curve px. We want to draw samples from this px. Okay, so let's the strategy like this. Let's try to upper bound it or enclose it using a function. Let's try to encapsulate it using a function. Let's say this function is this blue curve. And what is the property of this function? This function is some constant k times a known distribution qx. Let's say qx is a standard normal distribution with unity variance. Let's say qx we choose a proper value of k and place the normal distribution in such a way so that it encapsulates its upper bounds the target distribution px. Okay, so note one thing, that this constant k is actually very much necessary, because you see the area under this red curve is 1. If we just plotted qx k times qx, the area under it also would have been 1. Qx will never be able to enclose px because both the area under them is same. So if we multiply it by k, only then you can enclose it. Okay, only then you can enclose it. So the area under this will be k times 1, k. Area under this blue curve is k, and the area under this red curve is 1 because it is a distribution. So the constant k is very much necessary. You cannot do away with the constant. It's not possible that one distribution everywhere encloses the another distribution because area under it is same, unless they are identically same in all the places. So area under this, so you have to multiply by constant k to enclose it. Now what we do is that instead of drawing samples from px, which we cannot do, we draw samples from k times qx. Okay, and say those samples are kind of good approximation of samples drawn from px. But actually this approximation will not be good. Maybe if we can tight in the regions where the upper bound is tight, there the samples are good. But for example, in this region where the upper bound is this region where the upper bound is not so good, the samples are not, it's not a good approximation. Okay, so this will in general not give you a good sampling strategy. Let us try to do it this way. The region where the upper bound is tight, we take the samples, we accept the samples from there. And the region where the upper bound is not tight, we do not accept the samples from there. We don't consider the samples from there because they are bad approximations. So this method is known as rejection sampling. Okay. So in this picture, this red curve is the target distribution that you want to sample from, and this blue curve is an encapsulation. It's an upper bound on the target distribution P. Okay, you can also consider this as P hat because actually you will not get P. You will get only P tilde, not P hat, P tilde. So our procedure for rejection sampling is as follows. It's a two-step process. First, using the encapsulation distribution Qj, which is known. So this is Qj is known or standard, which we can sample from. Okay, using that, generate a sample Z0. Using that, generate a sample Z0. Okay, step one. So this is the first random number generation. Now you generate a second random number between 0 to 1. Okay, and look at this this ratio. So you have Z0, you know P tilde, so you know this height P tilde Z0. So this height is P tilde Z0, and we know also this height. This is KQ Z0. Okay, so you take the ratio of P tilde Z0 by KQ Z0. Take this ratio. Okay, so this is, since this is an upper bound, this will be less than equal 1. Since KQ Z0 is an upper bound, so you generate a random number between 0 to 1. Let's say we call this ratio R. If this random number is less than R, less than equals R, so basically you generate any random point in this one-dimensional interval. If the point falls in this region, that particular sample you accept and keep in your sampling file. Okay, and if it is greater than R, that means your sample falls, your second random number, not the sample, the second random number falls somewhere in this region, you reject that. Okay, you reject that. Right, so I have a two-step process. First, I generate using a known distribution Q, 1 point Z0, and then I generate a uniform random number between 0 to 1, a uniform random number between 0 to 1, and compute the ratio P tilde Z0 by KQ Z0. If this single uniform random number is less than this ratio, that is falls in the acceptance region, the white region, then the original sample Z0 that you keep, otherwise reject. Okay, so this is so maybe it turns out if you repeat this process for say 100 times, maybe you get only 30 samples that you can retain. The other samples you have to reject. Right. So naturally you see your rejection will be less in this region where the bound is tight, and the rejection will be much more in this region. So you will get more samples here and somewhat samples here and very less samples here. So the final set of points that you get after this rejection, the points that you retain, they will somewhat approximately represent the target distribution P tilde. It will represent the target distribution P tilde. So this is the principle. So naturally, you can actually show that this is unbiased. That means if you really draw large number of samples, the final set of samples that you get are actually distributed according to p tilde. But it is a bit inefficient because you have to throw away, you have to reject a lot. If you generate 1,000 samples, you only may be able to keep only 300 of them. Okay, so you are wasting time. Okay, so now let us ask the question that how many samples are getting rejected. So you see that, or rather, let's ask the question how many samples are getting accepted. So you see, since you are generating a Z0, and then along this line you are generating a point. Along this line you are and keeping if it is in this white region, rejecting if it is in this gray region. And if you do this for all values of Z0, you will see as if only the points which are lying in this white area that get accepted, and those who are lying in this gray area, they are getting rejected. So the fraction of points that get accepted is proportional to this white area divided by the gray area plus white area, which is so this is the area under the p tilde curve, and this is the area under the q curve, because that's the area under the blue. So gray plus white is the area under the upper bound, the encapsulation function kqz. Okay, so since p tilde is a distribution, the white area will be 1, and qj is a distribution, area under qj will also be 1, but since you are multiplying it by q, this area, this ratio will actually be 1 by k. So if k is your scaling factor, your acceptance ratio is proportional to 1 by k. 1 by k. Okay. All right. So one more thing is that, see, we are so far told that in the rejection sampling we have used p tilde, but your actual target distribution pz is 1 by some constant, say let's call it a into p tilde z. You usually call it capital Z, but I have already used z, so I'm not using it. Okay, so but we have drawn a sample from this by using it as a lower bound of some standard distribution kqz. The thing is that you can actually use it to approximate the original pz, because this a is also a constant, so this can be absorbed inside this factor k. This can as well be, you can as well write down that pz is less than equal to ak qz. Okay, so just the normalizing constant changes, the encapsulation scaling factor changes. Time this. Okay, so only your rejection ratio will alter, but you will get the same distribution. You will get the same distribution. Your rejection ratio will only change. So I mean, so basically you can also reconstruct the actual distribution pz, not just p tilde z. And we have seen that the acceptance ratio is proportional to 1 by k. So tighter your k is, better approximation, better efficiency you get in sampling. So this principle is known as the Monte Carlo approximation principle. Monte Carlo approximation principle. The principle is the following. Suppose you have a very complex shape. You try to encapsulate it within as tight standard shape. Let's say as tight a rectangle, as tight a square, or whatever. Using some standard shape, you try to encapsulate it, upper bound it. And if you want to find and then you generate samples which are inside you keep, samples which are outside the region you reject. And since the area under this is square or rectangle or whatever is known, the area under this complex shape can be found out as the ratio of number of rejected samples to accepted samples, or rather number of accepted samples to rejected samples. Okay, so if n samples get accepted and total there are capital N number of samples, and if the area under this curve is A, you divide it by the area of the square. Let's say it's a unit square, so 1. So you can find out this area A by fraction of samples which are accepted. And it's not just area. In fact, you can so this is a Monte Carlo approximation of this area. You can find out any other moment, say the moment of inertia or something, anything you can find out. So in general, you can think of area as an expectation. So you can, in general, if P is an unknown distribution, a complex distribution, and fx is any function, you can approximate this integral fx into px dx, which is nothing but expectation of fx with respect to px, by the fraction of samples fxi, fraction of samples which are accepted, and sum of their xi values. So you do a rejection sampling, and retain only the samples which fall in this region, and let's say m such examples fall in this region, and you add up the xi values, fxi values for all of them. You add up the fxi value for all of them and divide by m, and this number would be a good approximation of the true expectation of fx with respect to the unknown, with respect to the px. So this principle, so this is a very important. It can be, need not be area or just the distribution function. It can be expectation of any arbitrary function fx with respect to an unknown distribution px. Okay, so earlier I said that I want to reconstruct that distribution, but it can actually be shown if you can find expectation of any function with respect to that distribution. You actually know everything about the distribution. If you replace fx by just 1, you get the mean of the distribution. If you replace fx, by x square, you get the variance of the distribution, and this way you get all the moments of the distribution. In fact, you know everything about the distribution if you can compute this expectation. So this theorem forms the foundation of Monte Carlo approximations. So basically, the underlying principle is rejection sampling. You generate a sample within some encapsulated region. You check whether the sample is in the acceptance region or in the rejection region, and depending that you accept the sample or reject the sample. And finally, the collection of samples that you retain is a sample drawn from the target distribution, is a fair sample drawn from the target distribution px. Okay, so it's kind of an example. You use an auxiliary or a auxiliary standard distribution to draw sample from a complex distribution. In fact, there are many other ways. This is not just the only way. There are many analytical techniques. For example, there are at least 50 different ways you can generate random normal numbers or random student distributions. There are many ways. So there is a famous Box-Muller method, which says that if you go to the polar coordinate and you have a radius generated according to a uniform distribution, and you have your theta generated according to a multinomial distribution, then r cos theta and r sin theta, they are both Gaussians. They are bivariate Gaussians. So all this, there are different indirect ways or transformation ways. You transform by applying some, if x and y is distributed according to uniform, and then some fx and fy are distributed according to normal. So these are coordinate transformations. But in general, they are difficult. In general, they are difficult. I mean, it's analytical, so it's a case-by-case basis, not a general principle. But this rejection sampling or the Monte Carlo approximation always works, irrespective of what your distribution is. Maybe your efficiency will low, but it always works. This actually is an interesting history. So there was one person, Ulam, who was a friend of von Neumann, and he was playing the first game of solitaire. And well, he was an Italian, he was an intelligent person, so he wanted to find out how many initial cards would lead to a or a successful, and he analytically could not solve it. So what he did was he was randomly generating thing and actually playing the game. So that's an important thing. He was simulating the game. So that's what we are also doing. We are in some sense simulating the distribution. He was generating samples and then seeing that whether he actually wins or not. And from the fraction of wins, he came up with the probability that any random initial configuration will win. And then when he discussed this with von Neumann, they were solving some important atomic physics problem, whether the critical mass of uranium in the Los Alamos project. And then they had to do many complex integrations, which they couldn't. There were no computers at that time. There were no numerical methods, very, very rudimentary numerical methods. And this method caught the attention of von Neumann. And then he started using this this Monte Carlo method to solve those integration problems. So area can be thought of as an integration problem, those integration problems, and they become very successful. And since then, in lot of physics, lot of chemistry, lot of geophysics, these Monte Carlo methods are very interesting. Whatever complex distribution, complex function, you use it. In fact, there are many interesting articles that all these COVID predictions that you see, that how the disease will spread, these are basically Monte Carlo approximations. The actual function is pretty complex. Okay, so now let us come to our second method that we will use for sampling. So we have studied rejection sampling or Monte Carlo sampling so far. We now study the second method called a Markov chain, and we will use it for sampling. Okay, so let us consider a kind of a system like this. So there are states of a system. Let's say, let us take this example. There is a person who can be either in the left room. There are two rooms in a house, either the left room or the right room. And the person will be in one of the rooms at some instant of time. And in the next instant of time, she can change her room or stay in the same room. Okay, so in the Markov chain terminology, this room should be called states, and there would be a state change at every time step. The state change is governed by the following law, by something known as transition probability. So given the person is in room L, the probability in the next time step, she will be in room R, is denoted by this transition probability. I have written it down as TL to R. Let's say this transition probability is 0.7. So basically she tosses a coin, and if it is 0.7, she moves to the next room, R. And she can also decide to stay in the next room, same room, which is TL to L, which is 0.3. Okay, so it is a Markov chain because she really cares about where she is now. She doesn't care about, wait a minute, I think I have lost connection. I'll move to another internet connection. No, I don't have power since last night. I may lose connection very soon. I'll record it and upload it later. Okay, so that's what happened. A person is in some state, let's say L, and in the next time set, she can either move to the room with another probability, and all this stay in the same room with some probability. So now we can simulate this thing. we can simulate this thing. For example, if we just look at every time instance where the person is over time instance, then we'll see a sequence like this, L, L, R, R. So basically I am executing the or running the Markov chain, or the actual term is I am simulating the Markov chain with time steps, and then I'll get a sequence like this. Now, let me ask the question, what is the probability that C is in the room L after T time steps? C is in room L. So if we simulate this for T time steps, what is the probability that the last step is L? I am interested to find out this probability. Not that everything is probabilistic. It's not that C always goes from left to right. He tosses a coin, depending on the outcomes, he goes to left to right or stays in the same room. Okay, so let us look at this probability after T time step. What is the probability that C is in the left room? Let us start. Let's say initially C is in the left room. So at time step 1, we can think of as the probability that C is in the left room is 1. And the probability C is in the right room is 0. Then C transitions one step. So what is the probability? Again, C is in the left room, it is 0.3. And what is the probability C is in the right room? It is 0.7. Now look at the time step 3. Now what is the probability C is the left room? C can be in the left room in 2 different ways. Okay, one more thing, let me quickly write down. Sometimes these transition probabilities I'll write down in this way. So what is the probability C is in the room R given in the previous state C was in the room L? So I'll write it as this transition probabilities as conditional probabilities, where there is only one variable in the left of the condition and one variable in the right of the condition, because it is Markovian. And this collection of states and transition probabilities actually completely define a Markov chain. Okay, so how C can be in the third time step? How C can be in the left room? First possibility is in the second time step C was in the left room, and C stayed back in the left room. Other possibilities in the second time step C was in the right room, and then C came back to the left room. Okay, so this is in the time step 2, x2, C was in the left room. And time step C3 is the transition probability that C stayed back in the left room. Okay, this would be equal to L actually. So I'm in general line S3, you have to write x3 equal to L, x3 equal to R. The other possibility, C was in the time step 2 in the right room, and then C transitioned from the right room to left room. So basically, I am marginalizing over all previous state values that are possible. They basically represent different ways you can reach a particular state in X3. So these are the all different ways in which you can transition. So if you do this calculation, you will get something like this. So this can recursively be carried on, because see, all I need to calculate the probability of being in certain state in xk plus 1, all I need is where I am in xk and the transition probabilities. That's all I need. Okay, because it is Markovian. That's all I need. So at every step, this calculation length will be only these two marginalization. Okay, in this case. So if there are many other ways, see, if there is a top state from where we can live, there will be another term here. So the marginalization terms will increase. But you need not go back in time. You only need to go back one step in time. So at every step, I can keep on calculating these probabilities. And if we go on doing this, so see, so earlier I said when I simulated, I saw a sequence like this, I saw a chain like this. But this chain is not the only dynamical system that is changing. You can think of this as, since there are only two steps, you can think of this as a two-dimensional distribution. In this case, in the first step, the distribution is 1 and 0. In the second step, it is 0.3 and 0. In the third step, it is say in the third step, it is say point how much 0.4 something, some value and some value. So at every step, these two probabilities represent a distribution over a discrete distribution, in this case over the states. I have two states, so it is a two-valued distribution. It's like a coin toss. If I have a case n states, so this distribution would have n entries. And not only that, it could have been continuous also. So I can represent Markov chains not only in discrete distribution, I can also describe them. I am soon coming to it, how I can describe them over continuous distributions. So I have, yes, I still have connection. Okay, so what you observe that if I represent this two entry distribution as P, so I have one distribution at P1, the distribution changes at P2, distribution changes at P3. So it's not only this sequence is, as I simulate the Markov chain, not only this sequence is evolving, the observable state values are changing, but also this distribution over probability distribution over state values. That means what is the probability the person is in state 1, state L, what is the probability that the person is in state R at first time step, that is also changing with time. That is also changing with time. Okay, so these probabilities are also evolving as we advance in time in the simulation. And how they are evolving? By this simple calculation. You just need to find the probability in the previous state, and from that you know the transition probabilities, you can get the probability for the next step. I think this is clear. This I am not explaining anymore, how I have calculated this. So, so these probabilities are, so if we had more states, there would be more terms, say top, bottom, and there will be more probabilities. Say 0.2, 0.1, more probability. So basically each row is a distribution over different states. And this distribution is evolving with time. And what we will see is that if we have simulated for a long enough time, these probability values would kind of converge. They would stay same. So 0.42, 0.58, in fact, that's the convergence value for this. If you work out, they would stay the same. They would not change. So after you say 1 million times, if you simulate, the value becomes 0.42, 0.58. If you look at it after 2 million times, it is still 0.42, 0.58. So this thing is said to be a converging distribution. Note that this sequence will never converge. This is probabilistic. So it's not that it will get stuck in one state. It's not that it will get stuck in one state. This state will keep on changing, and depending on this coin toss probability, it will oscillate between these two states. But the probability of being in state L or state R, those probability they converge to some value P star. Okay, so another way of looking at this thing is like this, interpreting these probabilities is like this. Suppose I simulate one Markov chain for 1 million time and look at the last value. And another same Markov chain, again I simulate and look at the last value after 1 million times. So they will be something like, I said that they may change. Every time you run for 1 million, they may change. If we do this large number of times and see how many fraction are L and how many fraction are R, this relative, these values would give us that after time infinity, what is the probability the person is in L room, and after what is the probability the person is in R room. This probability would be, this fraction would denote that probability. And I think it is obvious, there is nothing surprising in it, that these probabilities, these converging probabilities P star will be close to these final probabilities. Okay, so this will, if we look at this, if we look at the number of states, count the number of states, get their fraction, they will actually be P star, the distribution P star, which is 0.42 and 0.58. Okay, in fact, you need not run several Markov chain. If you run one Markov chain for long enough, and discards, let's say the first say 1 million terms or 1,000 terms, and look at the rest of the values and see how many fraction are L, how many fraction are R, that ratio will also be P star. So this initial 1,000, these values we call a burn-in period, and this we call a asymptotic period or a convergent period. So if we look at the states in the asymptotic period, the relative count of L and R would be same as the converging probability P star. Okay, so this gives you a way of sampling. This gives you a way of sampling in the sense that if your P star is unknown, so another way of these state values I have looked at in the asymptotic period, they can be thought of as some kind of sample drawn from this P star because they follow P star. So these values can be thought of as samples drawn from P star. Okay, so that was my goal. So suppose P star is my target distribution or the desired distribution. I don't know, it's intractable. But if I can somehow get an Markov chain whose converging probabilities or absorbing probabilities is the P star. Okay, so it's kind of inverse problem. One is given a Markov chain, given the transition probabilities, what is P star, where it converges to. Second is, given a P star, what is the Markov chain which will converge to it? Is this the inverse problem? So if we can design a Markov, so suppose I look at this inverse problem. That means I want a target distribution P star. If I can generate design a Markov chain whose convergent probability is P star, then the asymptotic simulation of the Markov chain will give me a sample of P star. Will give me a good sample of P star. So this is also a sampling technique, and this sampling technique is called a Markov chain sampling technique. Okay. So the technique is simple. We start from initial distribution Px. Say we started with one in left and 0 in right. This is the initial distribution. Build a Markov chain. This is the critical state. This is what we will discuss in the next 2 classes. Build a Markov chain that converges to Px. Start from any state x0. You keep on generating xk plus 1 using the transition probabilities. And if you throw away the burn-in period and look at only the asymptotic samples, your samples will be a good sample, a fair sample from your target distribution Px. And this process is known as the Markov chain. I have included it from the discrete point, but as well, these states can be continuous. Let's say these states can be any point in R2. So the asymptotic samples that you draw in R2, so X will be a 2-dimensional point, they will form a kind of path. So as the Markov chain evolves, they will kind of form a path. They will go around. And the final samples that you get will come from your target distribution, where the Markov chain converges to Px. Okay, so our job is to, given a target Px, can we construct a Markov chain which converges to this Px. Okay. All right. So the next question is, does a Markov chain always converge? We said that it converges. So does a Markov chain always converges? So here is an example which doesn't converge actually. You see, even if we run for infinity time, it will always oscillate between left and right. So it's not necessarily that any Markov chain converges. there is another definition that we need. Every Markov chain has a distribution associated with it, which is a stationary distribution. What the stationary distribution means that, for example, this is a stationary distribution, this 0.4 to 0.58, because you see this is x 1 million is this. If you look at x 1 million plus 1, and if you follow this calculation, you will see it is again 0.4 to 0.58. If you just by hand, if you do this calculation for x 1m plus 1, it is still this. Okay, so if the distribution follows this property, that P is such that transition of x to x prime into px. So you are in x and you want to transit to x prime. This probability marginalized over all possible values of x from where you can reach x prime. This probability is same as px. So this 0.4 to 0.458 at the previous step, the distribution in the previous step is same as the distribution in the next step. Okay, that means once you are in that distribution, once you reach that distribution, you will stay forever in that distribution. It will not change, it will be stationary. And that is your converging distribution P star. So this, if P follows this property, then P is P star, your converging property. That's natural because it's stationary. Once you go there, you stay there forever. Okay, and so our Markov chain is, once you reach this stationary distribution, henceforth you can take your samples and that samples will reflect P star, because henceforth it will stay in P star. Okay, there is a theorem called the ergodicity theorem, which says that if the transition probabilities are strictly greater than 0 for all pair of states x prime to x, which basically means you can reach from any state to any other state, then the corresponding Markov chain will have a unique stationary distribution. And wherever you start from as your initial condition, as your initial distribution, you will always land up in this stationary distribution. This is the ergodicity theorem. We'll say the Markov process as, once it reaches the stationary distribution, it's mixed, or it has reached the mixing. It has become ergodic. So this is usually the true for most of the cases, but this is a requirement. Okay, so this is the basic principle of Markov chain based sampling. That means you want to sample from a target distribution P. You design a Markov chain so that P is the stationary distribution for that Markov chain. And then you simulate the Markov chain and throw away the first burned in phase, say 1,000 samples. And once you have thrown away, and henceforth, if you look at your simulation output, the state values, they will be a fair sample drawn from Px. So all you need to do is to design a Markov chain whose converging probability, absorbing probabilities, or stationary probability distribution is Px. We'll do that in the next class. What we'll do is that actually we will combine this Monte Carlo sampling with Markov chain sampling to design a more sophisticated method called Markov chain Monte Carlo sampling, MCMC methods. Okay, thank you. Any questions?